Okay, let's do this. Optimization in linear programming is a well-established field of mathematics. And it is a particular field of mathematics. See, in calculus, by the way, there are two kinds of optimization. There's the minimum and the maximum. In calculus, we have done optimization. When you have a curve, for instance, like that one, and you want to find the maximum or the minimum, you can use Fermat's theorem and find where the derivative is equal to 0. And then you can narrow down your search for maximums or minimums by looking at where the derivative is equal to 0 and then solving that equation. That is a well-known way of obtaining maximums and minimums. The problem is that if we have a piecewise defined function, and if the graph is not a smooth graph, if the derivatives do not exist, especially if they do not exist where we have maximums or minimums, then we have a problem. So if we have this kind of situation, for instance, then calculus is useless. We cannot use calculus any longer because calculus relies on precisely being able to find the derivative of the function, but this function has no derivative precisely at the point where we want to find the maximum or minimum. So we can't do calculus. There's two approaches to solve the problem of finding maximums or minimums. One way would be to smooth this out and convert this into a smooth function. So we would change the function into a smooth function and then apply calculus. That would be an approximation, by the way. The smooth function would be an approximation. And then apply calculus and use the approximation. To be perfectly honest, I do not know too much about that. But there's another method. The other method is using what is called linear programming. What this video is about, linear programming and optimizing. Now, there are two kinds of optimization. You can find a maximum or a minimum, but that would be the case in this area of linear programming. Now, having said that, there are different kinds of ways to set up a problem. We can set it up with inequalities, or we can set it up with equations. The typical way to do this is with inequalities, but we are going to use equations instead. Okay, so for a lack of a better word, normal or standard, standard problem uses inequalities, but we will use equations, but we will use equations. Now, we're still going to be looking at some kinds of inequalities, even though we're going to look at equations, but the inequalities have to do with the variables, not with the equations themselves. So the question is, what kind of problem are we going to solve? We're going to have variables. So the problem, we're going to have x1, x2, x3, x4, and you can have as many variables as you want to. So here we only have perhaps 4. I'm going to show you examples where we have only 2 variables and then 3 variables and then 4 variables in this video. So one requirement is that the x's have to be positive. They cannot be negative, or they could be 0, but not negative for sure. we will have a matrix equation. By the way, x will be the column vector x1, x2, x3, x4. So that would be x, a vector x. The matrix A is going to be as typically m by n, but m has to be, let's see, smaller than n. We want to have fewer equations than variables, and the reason is because we want to have more than one solution. And we're going to have a vector of constants b. So b will be b1, b2, b3, b4. By the way, I'm using 4 variables right now, but in the first examples, we're going to only use 2. So instead of having x1 through x4, we will have x1 and x2, and that's the end of it. Oftentimes, I'm going to call that x and y instead. Same thing with the b's and the matrices. The matrix. Yeah, so because we're going to multiply a x equals b, well, if we have 4 variables, that means that the n has to be 4. If we had 3 variables, then the n would have to be 3, and this would have to be 2 or 1. Whatever m is has to be smaller than n, and n is given by the number of variables, because we have to be able to multiply the matrix with this column vector to obtain this other column vector. But there's one more thing. So here we have a whole bunch of solutions because we have more variables than equations. We're going to have another vector c, c1, c2, c3, c4. And again, right now I'm using 4 variables. If we had 2 variables instead, and as in some of the examples we will have, then we would have only 2, 1, 2, 1, 2, 1, 2 instead. And there's going to be a whole bunch of solutions, but there's going to be one among all of those solutions which is going to be best. And we have to define what we mean by best. And we're going to want c dotted with x, this x and that c, to be minimum. Yeah. So there's going to be a whole bunch of solutions of this equation, infinitely many solutions. However, there's going to be one which is going to cause this dot product to be minimum. Yep. And that is essentially what we want. The difference between this approach and the standard or normal approach is that instead of this equation, they have this inequality. Yeah. Mind that this symbol technically as written doesn't make sense. This doesn't make sense as written because we haven't defined what we mean by one matrix or one vector being smaller than another vector. That doesn't make sense. And we can talk about the magnitude, but not, or the length of the vector, but not just a vector by itself. So this is a little bit of abuse of notation. What we mean by this is that every element on this vector is smaller than every element in that vector. So for instance, one requirement, this requirement here, may be written as 0 is less than or equal to x1, x2, x3, x4. Again, this is really abuse of notation. Technically speaking, that doesn't make sense. But what we mean by this is that, so we're giving a meaning to this, meaning that 0 is less than or equal to x1, 0 is less than or equal to x2, 0 is less than or equal to x3, and 0 is less than or equal to x4. So when we state that this has to be less than b, we mean that those numbers have to be uh, smaller one by one to the numbers corresponding to B. Now, this is our standard or typical or normal linear programming problem. We're not going to do this, so I'm going to cross that off for now, lightly. That doesn't mean that it's bad. Actually, that's the way most problems are presented. We're going to do this instead. Ultimately, they are related anyhow, so there's not much lost in this as we go from here to here. There is a process to solve this problem. Process to solve. Actually, it's an algorithm or algorithm. And it is called the simplex method. Simplex method. If you search for the simplex method, you are going to find a bunch of sites, I'm sure, where they show you the algorithm, the process. But I don't want to show you the process as an algorithm. I want to show you where the solution may come from instead, so or the why. So in this video, I'm going to try to show the why of the method and not the method itself. It is I have a little analogy, if you have ax squared plus bx plus c equal to 0, x equals opposite of b plus minus the square root of b squared minus 4 times ac. All of it over 2a, everybody knows the quadratic formula, but the question is why? You may be very good at figuring out your solution, but without having too much insight of why it works. So instead of just giving you the algorithm or the process, I want to show you a little bit of why the method works. The algorithm and the process you can find just about anywhere. It's why this process is widely known. There's a lot of history, especially in the United States, about how the process came about and is developed, and it has many, many uses. All of this optimization, by the way, the linear programming and optimization has many, many applications in businesses, logistics, I mean, you name it. There's a whole number of places where it is used extensively. We're not going to worry too much about the applications, even though this is an application of linear algebra, the applications of the optimization, we're just going to look at it from the linear algebra point of view. By the way, that happens a lot. You have a math topic, and oftentimes the application of a math topic is another math topic, and then the application of that is another math topic. So oftentimes you have to go through several layers before you actually get to a real application. So this may continue a few times until you actually are down to the bolts and nuts of a real application. And there's a good reason why we don't necessarily go into the real application, because we're studying mathematics. We're not studying the real application as some people may do in engineering. And the other reason is because a real application actually has many, many variables. A real application is actually many problems put together. And so we don't want to spend time looking at all the different little aspects of the application. We just want to focus on the theory behind the application. All right, so let's start with a problem. So let me divide this, because the kind of examples that I'm showing you are the kind of examples I expect you to be able to do in assessments, quizzes, tests. All right, so example 1, and we're going to divide this into A, B, C. Actually, there's going to be different sub-examples of this one. So the main idea here is that we have an equation x plus 2y equals 10. So we want to find solutions of those so that, so find solutions or solution x comma y, which oftentimes I will call it x. By the way, this is really a column vector. I should probably rewrite this as x equals xy. That's a little better. So that if, and here's the A part, C is equal to 2, 1, then C, so this is a vector. Again, I should probably put it as a, there, that'll fix it. So this is a column vector. So C dotted with X, yep, C is a vector, is minimum. See, there's hundreds of solutions. So for instance, if X is 2, then Y can be 3, and then you get a solution. But that doesn't necessarily minimize C dot X. Okay. So see, let's try to understand what is going on here. So there are many solutions of this. For example, 2, if X is 2 and Y is 4, oh, I said 3 earlier, but it should be 4 because that would be 8 and 2 is 10. That's one solution. Let's see, another solution could be, let's see, 4, 3, because 2 times 3 is 6 plus 4, 10. Another solution is 6 and 2, 8 and 1, 10 and 0. You could even go 12 and negative 1. Or going the other way, you could do 0 and 5. Or you can go negative 1. So negative 1 for X. Well, let's do negative 2. That'll make, I don't want to introduce fractions. So negative 2, 6 will do. Okay. First of all, this guy has to be avoided. No. No to this. No to that. Right away. Why not? We want solutions that are non-negative. This has a negative in it. Get rid of it. This has negative in it. Get rid of it. We don't want solutions. Only positive solutions. Now, by the way, this product of CX, we will call this the cost. The cost. So we want to minimize the cost. All right, and the cost is the dot product of this vector with 2, 1 with those. So that really means 2x plus y. So the cost, which is 2x plus y, when we multiply xy, see, if we multiply 2, 1 times xy with the dot product, we end up with 2x plus 1y. There we go. So we want the cost to be minimum. So 2 of those, so that's 4 and 4 is 8. The cost will be 8 here. The cost here will be 2 of those and 1 of those, so that is 11. So that's going up. 12 and 2, 14, 16 and 1, 17, 10, that's 20. So all of those numbers are large. 0 and 5 is 5. Interesting. This is actually the lowest we've seen. Is there any lowest? I don't think so. I think this is, so The solution to minimize the cost is this point, 0.5. Now, geometrically, what is going on is, okay, now this is the cost equation. Do not confuse the cost equation with the original equation. Sometimes they're similar. The original equation is x plus 2y equals 10. X plus 2y equals 10. So if we graph this, x will be 10 here, when y is 0, and then when x is 0, then y is 5. So about there. So we have this straight line, and we don't go beyond that because we don't want negative solutions. And there is an infinite number of points. Those are only a few of them, like 2, 4. 2, 4 is here. This is 5, by the way. And then, 4, 3, it's somewhere in here. 4, go 4 to the right, 3 up, and there you are. They're on the line. So there's a whole bunch of solutions which are going to be on this line. Now, if you take into account C, which is 2, 1, 2, 1 is this vector, 2, 1, which puts more value into the x, more cost. Now remember, this is the cost vector. So it puts more cost. Pretend that every x you spend is $2, and every y you spend is only $1. So x's are more expensive than y's. That is what this is telling us when we do the dot product. So that vector is this way, which means that it is more expensive to go in this direction than in any other direction. That tells us that going in this way, the cost is going to be greater than going in any other way. See how this is tilting to the right? So again, going towards the 10, which says it in here, is going to be very expensive. We're going to end up paying $20. As soon as you put money into this, then things become a little more palpable, more real to us. So again, if you put dollars here, this option of going with 10, 0 is going to cost us $20. But if you go with 0.5, which still solves the equation, we still solve the equation, which is something that is a requirement, 0.5, that's only going to cost us $5, because for every y we pay $1. That's what this says. Every y you pay $1, every x you pay $2. So this is way cheaper than going this way. So the solution that satisfies this equation, while being as inexpensive as possible, is this solution. So the solution will be 0.5. There is our solution. That's the solution. And the cost, the minimum cost, is 5, which goes with that solution. Okay. So that was part A of this example. By the way, before I move on into part B, I just want to rewrite this as a matrix. So the matrix is a 1 by 2 matrix. We have 1, 2, 1, 2. That's matrix A times x, y. That's the x equals B. B is just the 10. So this is a super, this is the matrix x, or the column vector x. So there's our equation. And the cost is the vector 2, 1. 2, 1. Okay. So this is the setup, and we want to minimize the cost. Sometimes we want to maximize the profit, in which case the vector would be P. Yeah, so, and that's easy to fix. Instead of spending $2 for every x and spending $1 for every y, if we were to earn $2 for every x and earn $1 for every y, then it will be in our best interest to have more x's, because then we would earn more money, because we earn more per x. But right now, I'm not going to go into profits. We're just going to go into costs. We want to narrow this down as much as possible because this is a new topic and we don't want to overcomplicate it. All right. So sub-example B, still in example 1. So I'm not giving you a formula necessarily. I'm just showing you why it works, but that is sufficient. The knowing why is sufficient for us to come up with a solution. Some students are very frustrated when I don't give formulas because, okay, what do you want us to do? Well, I want you to find a solution. But how? Well, that's the idea, you know. I mean, I don't mean it in a bad way. I don't mean it in an unscrupulous way, you know. But figure it out. That's part of what this is about. Okay, so let's have the same equation: x plus 2y equals 10, for which there are many solutions. And now we want a new cost. This is why this is B. This was A, the first one we did. We just finished. B, we're going to change the cost vector. We want it to be now 1, 1. So we spend the same amount of dollars on X or on Y. We want to be able to solve this equation while we minimize how much we spend on each one of them. Okay, we could go back and actually we can say the cost formula will be different. Instead of 2, 1, you know, 2 of those and 1 of those, $2 for each one of those and $1 for each one of those, we would have to do 1 and 1. So that would, the cost in B, the cost of this would be 2 and 4, 6, 7, 8, 9, 10, 5. So even though we're using, okay, so this is same kind of picture and all of those are solutions, but the cost vector is more of a 45-degree angle, and still that says this is a better deal than that, because yeah, way better to do this, because if we're gonna pay the same for both, for any one of the x's or the y's, then still we're better off with having few of either. And by having the 0, 5, we have as few as possible. If we had 10, 0, we will have very many of them, of the x's and y's. And by the way, you may say, well, what about in between? Let's say 8, 1 is one of the answers to this equation, you know, 8, 1. But then the cost here will be $9. Again, pretend that's dollars. So $8 for the x's, $1 for that one y. So that makes $9. That's more expensive than $5. So this is our best bet, just by looking at this. C, part C, still problem 1 or example 1C, same equation. Now the cost is going to be different. Initially in A, our cost was 2, 1, 1, 1. How about 1, 2? Cost equals 1, 2. So $1 for every x, $2 for every y. That's interesting. So now the cost goes this way. It's very high on the y's and low on the x's. So then we might have to go down this way, even though we end up paying more. This is interesting. We end up with more x's by sliding this way, because the x's are less expensive than the y's. Then we may be better off going that way. But you know what? Let's do this with a table. Let's be a little systematic for the x's and the y's. So 0, 5, again 2, 2, and 4. Yep, 4, and 3. There are more numbers in between. I just don't want to deal with the fractions right now. 6, 2, 8, 1, 10, 0. What is the cost associated with this vector? The cost is $1 per x, $2 per y. So the cost here is 10. 1 and 2, 10. Oh, it's $10 regardless. This is an interesting example. So it doesn't matter where we are. We're gonna end up paying the same no matter what. So here, the solution that minimizes cost is, well, we can, so if y is free, then x would have to be 10 minus 2y, and then just y. So that, and it doesn't matter which one you use, where y can be anything. So as long as y is between 0 and 5, we're good. So there's an infinite number of solutions, as opposed to this one, where we had only one solution. The solution is just this guy. That is the solution right here, no more. And by the way, the cost associated with that solution is $6, no, $5 still, $5. Here the cost is $10 regardless. Now, if we make this cost vector more steep, such as 1, 3, so example D, yeah. So the cost is even steeper. So every time you buy a Y, you are paying more. So cost equals, no, the other way around, 1, 3. Yep. Then, and we still have the same equation, x plus 2y equals 10. Let me copy this real quick, the x, the y, and the cost. Will be 0, 5, 4, 3, 2, 1, 0, 2, 4, yep, 6, and then 8 and 10. That's a zeros. Then the cost. So this says for every y we have to pay $3. So here we got to pay $15. 12 and 2, 14. 9 and 4, 13. 6 and 6, 12. 3 and 8, 11. We pay nothing because there's no y, and we pay $10 here. So that is our cheapest cost, our least cost, and that will happen here. So the farther away from the vector, the cost vector we are, in a way, the less expensive our option will be. So the solution, there are an infinite number of solutions to that equation, but the solution that is least expensive to us is this one, 10, 0. Yeah. Now, this is one of the easiest problems we can put together because it has only one equation. That's it. So keep in mind, this is one of the easiest problems. They do get much, much, much complicated. I plan to do in this video no more than 4 variables. A standard problem in applications, in real applications, people who actually do this for a living, I don't think I don't think I exaggerate too much if their matrices are at least 10 by 10, more like 50, in the 50s or 100 elements. So of course, they're not going to do this by hand. They use a computer, but they still have to understand how everything works. So this is a small scale of the kind of real optimization problems people do. And if you look, man, there are so many places where optimization has been used. it's not even funny. In the United States, in many other countries as well. Okay, so that was my example 1. Let's move on to an example 2. And there's going to be, again, different costs. So example 2. I'm looking for my equations. Oh, I put them in a wrong page. So the first equation is going to be 10x plus 5y plus z equals 10. My second equation is 12x plus 4y plus 3z equals 24. Okay. This is a plane in 3 dimensions. So it's not just like a little triangle as example 1. The picture is much more complicated. So we have 3 dimensions here, x, y, z. By the way, this is the same thing as x1, x2, and x3. I just, instead of putting little indexes, I just put x, y, and z. So when those two are 0, well, let's start with z. When those two are 0, when x and y are both 0, then z has to be 10. Yeah. So up here, pretend that is 10. And when those two are 0, then x is 1. So pretend that is 1. And when those two are 0, so pretend those two are 0, then we end up with 5y equals 10 divided by 5, y equals 2. So we have a 2. So we have a plane that crosses the first octant, and this plane actually keeps going through this wall, and through the floor, down, to the right and to the left. We just want to see this portion of the plane because one of the requirements is that all the variables are positive or 0. They could be 0. That is just the first equation. So this is the first plane. The second plane is similar. When those two are 0, z is 8. So we are lower. That's 8. And then when those two are 0, 12x equals 24. So that means x has to be 2. This is not totally proportionally correct, but that's okay. And then when y is non-zero, but the other two are, so 4y equals 24, that means y has to be 6. So way out here somewhere. So then we have this triangle. But this triangle cuts into this triangle, the first one. So this plane cuts into the other plane. Yeah. So now the picture is more complicated. They overlap in this line. Okay. All right. So when we are solving, and that means finding the solutions to the overlapping of those two, that means finding this line. This line keeps going on this direction, this direction. Of course, we only care about the portion in between because that is the overlap, but rather that is when both when the 3 of them, x, y, and z, are positive. So mind, a requirement is that x is positive or 0 and y and z. Okay. So there's many solutions here. Among all of those solutions, we want the one that minimizes the cost. And you may be asking, well, what is the cost? It depends how much we pay per variable. Sometimes x's are more expensive, sometimes y's are more expensive, sometimes z's are more expensive. So I'm looking for my cost. I can just, so a common cost I use, but don't think that all the costs are this way. So part A of the problem, assume the cost vector is 1, 1, 1. So we pay $1 per every X, $1 for every Y, $1 for every Z. And this line is inclined. Here there's going to be no Y's, so we don't pay anything for the Y's. But I don't know. My guess is that the solution is going to be here on the left because this is tilting up if my picture is correct. But we don't want to rely on the picture because it could be off. Not to mention, even if it was perfectly correct, the perspective of the picture may not be correct. When you draw a picture, even though the perspective is, or the measurements are correct, because of the perspective, because of the angle we're looking at it, something that may look as going up actually may be going down instead, or something like that. If I had to guess, the answer is here, but let's find out. Okay, so this is part A. With this cost, of all of those solutions, which one has the least cost? Okay, this problem is already difficult. And again, I'm not giving you an algorithm. I'm not giving you a process, a formula. If you search, you will find there's tons of places. And one of the things I don't like, having said that, is that the formula in one book is slightly different than the formula or the process or the algorithm in a different book, which is different than the formula in a different book or the process. They change a little bit. And that's why I don't want to focus on the process. I want to focus on understanding what's going on here. And that's what we are doing. So let's start solving this equation, this system of equations. By the way, the matrix, yeah, this is an important thing that we have. A, in this case, is going to be 10, 5, 1, 10, 5, 1, 12, 4, 3. The X vector is going to be X, Y, that's an X. Z, it doesn't matter whether I use round parentheses or square brackets. It's the same thing. B, the vector B is just the 10 and the 24. And the cost vector is 1, 1, 1. So what we are doing is solving the equation A X equals B, and there's going to be millions of solutions, but we want to find the one solution that causes the cost according to this cost vector to be minimum. So we're going to pay $1 per each one of the variables that we are going to use. By the way, 1, 1, 1 is a vector coming out this kind of towards us a little bit, coming this way. It is difficult to draw here, so it's 1, 1, 1. So yeah, 1, again, 1, then maybe 1. So it's kind of difficult. And then which one is the farthest one is not so obvious anymore. From that perspective, it almost looks like this is closest. We don't know. Let's figure this out. That's why we need to do the math, because just by the picture, and this is example 2, example 3 gets even more complicated. Just the picture won't be sufficient for us to figure out a good answer. A picture or a table is acceptable, I would say, for a problem that is this simple. One equation, no problem. One equation and only 2 variables. One equation with 3 variables is already more complicated. But 2 variables, yeah. So let's see. So we want to solve the equation, the augmented matrix. Yeah, we want to solve this equation. Matrix will be 10, 5, 1, 10, and then 12, 4, 3, 24. So we're going to do elementary row operations to come up with a row echelon form, row reduced echelon form um, of this matrix. I don't want to necessarily show you the steps. The one thing I want to say though is, personally, I don't use fractions until the very end. I try to avoid fractions. So instead of going, making that a 1, what I do is I make this a 60. Let me. This is not a very good. This is the work I did before. So there's my original matrix, although it's not nicely written, as a matrix. But then notice that the first step I did is multiply the first row by 6. The second row I multiplied it by 5. So those two match, and then I can get rid of the one of the 60s by just subtracting one minus the other. So this is not necessarily a very, very standard way of going about solving the matrix problem, coming up with the row reduced echelon form, but it doesn't use fractions until the very end. So I'm going to pause for a moment the video. You're not going to notice the pause because it's instantaneous to you, the person watching it. I just want to make sure my matrices, the matrices on my other page are correct, and then I'll just put the row reduced echelon form matrix here. Okay, so we end up with this row reduced echelon form, row reduced echelon form matrix. What does that mean? It means that x plus 11 over 20z equals 4, and that y minus 9 over 10z is equal to negative 6. In turn, that means that x is equal to 4 minus 11 over 20z, and y is equal to negative 6 plus 9 over 10z. Now, z has to be positive. So the most x can be is 4, because we have to subtract some z to this 4. And see, let me write this down. So the vector x, y, z, which is our solution vector, is 4 minus 11 over 20 z for the x. For the y, negative 6 plus 9 over 10 z, and then z. Now, before we go farther into this, actually, let's go farther into this. We can rewrite this as 4 negative 6, 0. Yeah. Plus z, 11 over 20, 9 over 10, and 1. Yeah. 4 negative 6, 0. In the picture, what that means is that if we go 4 negative 6, yep, think about that. 4 negative 6, 0, that means that if you keep going, take this line back here, eventually it's going to hit the floor, because this is, so it's going to hit the floor here. And when it hits the floor, it will be 4 negative 6, 0. And then this is the direction vector that goes from here in this direction. So, but we can only use this zone. We cannot just use all the numbers. So when we're using z as a parameter for this line, z has to be, it has to work in such a way that that we are in this region. We cannot be past that because then the x has to be negative. We cannot be before this point, whatever it is, because then y has to be negative. So there are some restrictions, and the restrictions can be drawn from this. So this guy has to be positive. Let's think about that. So 4 minus 11 over 20 z has to be greater than or equal to 0. We can move this to the other side of the equation. So 4 is greater than or equal to 11 over 20 z, and then we can multiply by the reciprocal. So z, that's a z, has to be less than or equal to 80 over 11. 80 over 11, but it has to be at the same time greater than or equal to 0. So 0 is less than or equal to z, but z has to be less than or equal to 80 over 11. But there is more to it. So that's just from this guy. There's another restriction involving y. So that is a restriction involving x. Because of the x having to be positive, x cannot be too large, because if it was too large, if z was too large rather, then we would end up with a negative x. We would have to subtract a lot. I'm just double checking. If I put 80 over 11, so the 11s cancel, yep, we end up with 4 minus 4, 0, which is the least this can be. And z has to be greater than 0 because of that. All the variables have to be greater than or equal to 0. Okay, so there's one restriction, and that is additional information we have, or restrictions we have to keep in mind. On the other hand, negative 6 plus 9 over 10 z has to be greater than or equal to 0 as well. So the y has to be greater than or equal to 0. Okay, so that gives us further restrictions on the z. We can put the 6 over, so I'm going to continue down here. 9 over 10 z has to be greater than or equal to positive 6 multiplied by the reciprocal, semicolon. So z has to be greater than or equal to 60 over 9, which is the same thing as 20 over 3. Yeah. So that means that z has to be bigger than a number, not only bigger than 0, but it has to be bigger than this guy, 20 over 3, but it has to be also smaller. When I say smaller, I mean smaller than or equal, or bigger, I mean bigger than or equal. I'm just being a little lazy on the tongue, but I'm actually writing down the equal. So we have to be less than 80 over 11. Yeah. As a mixed number, what we have is that this has to be, z has to be between 6 and 2/3 and 7. 11 times 7 is 77, so there's 3 11s left over. So z has to be between 6 and change and 7 and change. Z, back here, 6 and change, 7 and change, that creates those two endpoints within this octant, between those two triangles. Yep, so that produces the two. Now, which one of the two, or which point in between, because we have all the numbers in between, minimizes the cost. Okay, so let's write down C dot x, which is, in this case, remember, this is part A, 1, 1, 1. So each variable is going to cost us the same. X, Y, Z, by this we mean the vector X. So that is 1, 1, dot product, 1. And then X, Y, Z will be, we still have it here, 4 minus 11 over 20 Z, negative 6 plus 9 over 10 Z, and then Z itself. And we're doing the dot product between those two vectors. So remember how we do the dot product, multiply this times that, this times that, this times that, add all of those together. So C dot X is 4 minus 11 over 20 Z. Well, we're going to add negative 6 minus 6 plus, anticipating we're going to add those two fractions. I'm going to turn that into 20, 18 over 20 Z plus a single Z. Again, anticipating we're going to combine the Z's together, we're going to add 20 over 20 Z. So all of these Z terms have the same common denominator, 20. So that is negative 2. We got 20 plus 18, 38, minus 11. 38, that's 27. So plus 27 over 20 Z. Okay, now I want you to please think about this. This is the cost. Cx is what I call the cost. The cost is this. Now think about that. This number is positive. Whatever it is positive. And what happens if Z is big or bigger than any number? So say Z is 1. If Z is 1, this number, this fraction multiplies with 1 and then adds to negative 2. If Z is 2, this number multiplies with 2, doubling this portion. We still have to add to negative 2, but now we have more of the whole, of the entire thing. If Z is 100, well, to make the math easy, if Z is 20, then we got the 20s cancel, and 27 minus 2, 25. So the cost would be 25. If Z was 40, just to give you an example, then we'll have to simplify. 2 times 27 is 54, minus 2 is 52. So on one hand, we have 25. On the other hand, we have 52. So I hope it is clear to the viewer that the bigger the Z, the more cost we have. The reason is because we're adding a positive number times Z. So again, the bigger the Z, the more cost we will incur into. So to minimize this output, to minimize this output, Z must be as small as possible. Yeah. Think about that again. If Z is big, the whole thing is big. If Z is small, now you can say, well, can Z be negative 100? No. Why not? And that's why we had to do this. It's on this page. Z is bounded by 20 over 3 and 80 over 11. We're bounded by this guy. Yeah, we're bounded by this guy. So the answer Has to be by the smallest value we can obtain. So the smallest value is 20 over 3. Again, this is important. This is the restriction on the z. So the smallest z we may use is z equals 20 over 3. 20 over 3, which is the same thing as 6 and 2/3. Okay. So what is the answer? Because we want the vector that gives the answer. So the answer is, here it is, 4 minus 11 over 20 times that z value. Oh, 20 over 3, negative 6 plus 9 over 10 times 20 over 3. And z itself, which is 20 over 3. So we need to simplify those fractions, those additions or subtractions. Let's see. That is going to be the 20s cancel. So that is 12/3 minus 11/3, 1/3. 20 and 10, it's simplified down to 2. Times 9, 18 over 3, 6 minus 6, 0. 20 over 3. So here's the solution. Here it is. That's what minimizes the cost. What is the minimum cost? Minimum cost is, by the way, some books don't use this x. The x is the variable x. This is the actual solution. So maybe I'm going to call it xb for best. There's many x's, but the best one, I know it's a little confusing, but it's the best one. Some people put a star, or we want to differentiate it. We don't want to put an apostrophe symbol because then that may look like a derivative. I'm just going to call it best. I just made that up right now on the spot. The minimum cost is going to be 111 multiplied with the best 1/3, 0, 20/3, and that's actually going to be 1/3 plus 0 plus 20/3. That's 21/3, which is 7. So pretend this is money. The minimum cost is going to be $7 if we want to fulfill. So the problem started here. Example 2a, if we want to fulfill these requirements, if we want to solve these two equations at the same time while minimizing the cost, if the cost is $1 per variable, per x, per y, per z, then the way to minimize the cost is to go 1/3 on the axis, 1/3, so there is 1, so 1/3, no y, so we don't deviate to the right or to the left, but then we go up by 6 and 2/3. So actually, what we found is this point. Inadvertently, this point is 1/3, 0, 20/3. This point on the left. Now, don't assume that the lowest point is the answer. It depends on the cost. So right now we used x and z, but we did not use y. But let's say the x's and the z's are more expensive. Let's say they were more expensive than the y. So let's say, okay, so this is part B of example 2, part B. I'm getting excited because this is fun. All right, so let's say C. Okay, so the answer here was has no y's. A little bit of x, a lot of z. Actually, let's change. I was thinking to use 2, 1, 2, but let's say x's are $1 each, y's are $1 each, but let's put more value in the z's. Let's say the z's are $2. They're more expensive now. Are we gonna, is this gonna minimize the cost? Now, we don't expect the cost to still be 7. The cost will be completely different, perhaps. But regardless, there's going to be a minimum cost. Okay, once you do part A, part B is not too bad as long as part A is correct. Okay, so from part A, okay, actually, I'm going to use a new page because I don't want to run out of space too soon. Okay, so from part A of problem 2, we have that x, y, z is equal to, I still have it here, 4 minus 11 over 20 z, 6 plus 9 over 10 z, negative 6 rather, and z. Okay, and z is between, I have to look for it. It is between 20 over 3 and 80 over 11. Okay. So what is the cost? The cost is the dot product between this new cost vector, $1, $1, $2, where the z's all of a sudden became more expensive. Now think about it. You know, let's say we're importing articles or items, you know, I don't know, sweaters. You know, we're not making sweaters, we import sweaters, and, you know, China and Vietnam and I don't know, and Honduras and, you know, other places, Mexico, even Canada, perhaps. Um, you know, and then all of a sudden, in one of those countries, for whatever reason, you know, they have to increase their price. You know, if they want to maintain a solution, a supply, for instance, some kind of supply, you know, we might have to weigh things differently. You know, instead of buying too much, you know, here we're buying nothing from, I don't know, let's say Mexico. But then if these guys become more expensive, then maybe we have to go back and say, hey, we want to produce more in a different factory. Now, this is not necessarily true only for countries. It could be states. What if Wisconsin became more expensive, or Michigan, or Louisiana, whatever, you know, Alaska, it doesn't matter. This is the nice thing about the problems in the abstract. We don't know, and we don't necessarily care which one it is, but I'm just trying to give you an analogy. If the Z's became more expensive for whatever reason, how does that change how much we're going to buy of each? So let's say we got 1, 1, 2, 1, 1, 2 instead of 1, 1, 1, and we're going to multiply with x, y, z. So, you know, I guess I'm going to do this in 2 steps, x, y, z. All right, and that's going to be 1x, which is one of those, 4 minus 11 over 20 z. 1y, so one of those, plus 6, oops, minus 6 rather, plus, again, anticipating we're going to do 20s, 18 over 20z. Okay, but here's the difference. Plus 2 z's, so 2 of those. If we are using a denominator of 20, that means we have to add 40. 40 over 20, that's 2z. I'm just thinking, so 4 minus 6 is negative 2 plus 40, 58 minus 11. 58 minus 11 is 47 over 20z. So our cost, you know, I'm pausing for a moment because I'm thinking, well, this cost, as long as this number is positive, this sum is positive, then the smaller the z, the better. So what z causes this to be smallest, that's got to be the same answer. So even at $2, which puzzles me, that means that almost doesn't matter what if this was 0, if the cost was 0, which is the smallest cost we have, because the cost is always positive, no matter what, it doesn't matter. Yeah, so it doesn't matter what the cost for the z is. Our best answer will always be with the smallest z. Yeah. Yeah, so this quantity is minimum when z is as small as it can possibly be. And the smallest that it can be is 20 over 3. Yeah, so 20 over 3 puts us at 47 over 3. Yeah. So the answer is the same answer because the 20 over 3 corresponds to that. So the answer is still 1/3, 0, 20 over 3, and the cost, the minimum cost at minimum cost, which is -2 plus, if we plug in 20 over 3 for z, the 20's cancel, 47 over 3 minus 6 is 41 over 3. So if we divide 39 is 13, 13 and 2/3. So our cost went up to $13 and 2/3 of a dollar. So the fact that Z became more expensive did not change our most optimum way of doing this. So let's say Indiana, I'm just making things up, you know, a factory in Indiana became more expensive for whatever reason, you know, a tornado went by, or I don't know, you know, or the electricity went, I don't know. And so even if Indiana doubled the price, just to say something, let's say Z was the Indiana factory, we still have to produce the same number of items in the same way. So the question is, what cost vector would actually cost us to change the output, to have a different output? Okay, so here I'm looking at this and I'm thinking, okay, how can we get a small z if if X became very expensive, let's say $4 per X, and the other two remain as 1 and 1, that I believe will do it. Okay, so example C of problem 2. Okay, say the cost was 411. So $4 for every X $1 and $1. I want to be safe. Let's just say $6. Sorry about changing that. I think that will change the scale. All right. So what is XYZ? Based on problem A, we have 4 minus 11 over 20z. And I might have to change this again, make it super duper expensive. I'm almost want to change it right now, but I'm not yet. So negative 6 plus 18 over 20z, and then of course 20 over 20z. Please do not get confused. I'm already changing that into 20s. So multiply by 2 the top and the bottom, multiply by 20 over 20, and that's how I get this. And the cost, if the cost is this, we got to do the dot product between those two. Let me do a quick math here. So if I multiply 6 times 11, I get 66. Negative 18 and 20. Okay, I think that will do it. That will have to change things. So if X's were very expensive, $6 a piece, how would that change our solution? Well, the cost, Cx, C dot X, is this vector times this vector, this times dotted with this. So 6 of those, 6 times 4 is 24, minus 66 over 20z. One of those, minus 6 plus 18 over 20z, and one of those, plus 20 over 20z. Man, that makes a good problem. So 20 minus 6 is 18. Okay. Now, negative 66 plus 20 is negative 46 plus 18. I'm just going to do this because I don't want to make a mistake. Minus 18 minus 20, negative 28, if I'm not mistaken, negative 28 over 20z. Of course, we want to simplify that. 18 minus 7 over 5, or 1.4z. Okay. Okay. This is very, very good. Now, think of this quantity. This is the cost. 18 minus, see, here's the difference, minus that. If we are subtracting from 18, and this is our cost. This is the cost in dollars. What is in our best interest? Of course, we want to pay less, which means that we got to take away as much as possible from 18 to reduce our cost. So we can say, to minimize cost, comma, we need to make z as large as possible. Okay. Now, in a previous problem, we did have boundaries for z. I forgot to put it here. 20 over 3 is less than or equal to z, which is less than or equal to 80 over 11. So this time we want z to be as large as possible, 80 over 11. And that changes the whole point. Okay. Z must be 80 over 11. Okay, new page. So what is our solution? Our solution is XYZ equals 4 minus 11 over 20 times 80 over 11. This has to be 0. And that the reason for that is because the X became too expensive. See, if we are making, I don't know, producing things, and one factory just went bizarre and said, hey, we're going to charge $6 a piece, while the other two factories only charge $1, then we're not going to order any from that factory. Now, that is not as obvious or trivial. Remember example B? The cost for Z went up by double. We double. It was 112. Even with that additional cost, the production by each one of the factories, if we kept it the same, that still would minimize the cost. So just increasing one of them doesn't automatically mean we have to change the orders. Yeah, we have to do the math. That's what it boils down to. We maybe things will change if things go in price, but maybe not. Now the math is not going to be so simple here. -6 plus 18 over 20 times 80 over 11. Okay, so that's going to be 4. 4 times 18, 72. 72 minus 66. I don't want to do that in my head. 72 minus 66 equals 6. Yep, so 6 over 11. And then Z has to be 80 over 11. Okay, so that puts us on the other point. I'm looking at my graph. That puts us on this point here. Here. This point on the other extreme has coordinates 0, which makes sense, no x, 6 over 11, and 80 over 11, which is 7 and change. It makes sense that is 8, so that is closer to the 8, but not quite. So we have to shift production. But that's the thing. If you guys are in engineering or in trying to figure out the best cost, just because one factory became more expensive, it can be in the same town. I mean, I was initially talking about countries, but then I went to states, and if we live in Grand Rapids, one factory may be in Grand Rapids, another factory may be in Kenwood, another factory may be in Holland. If one of the factories doubles, that doesn't necessarily mean we have to shift the orders from the factories. The only way to know for sure is to do the math. That's what it boils down to. So if the cost all of a sudden went to $6 here, $1 and $1, well, we're going to order 0 from that, and then 1 from each one of those. So the minimum cost under this cost structure, minimum cost, is going to be 6 of those, 6 times 0, plus 1 times 6/11, plus 1 times 80/11. See, and that is going to give us 86 over 11. So that is $7 and 77, 9/11, I believe. Yeah, of $1. So we're going to pay more than if we had 111. If this one went to $6, because I remember A was 111, if I'm not mistaken, $1 a piece. Yep, there's A, part A. And the minimum cost was $7. So if all of a sudden X went up to $6 a piece, in this case, we cancel all the orders from that factory that is going up, and then we use the other two factories instead. And that increases the cost, but not too much. In part B, when Z was $2 a piece, which is not a super dramatic. Now I want to know how much was our cost there. Did I figure this out? Yeah, it was $13. Whoa. So even though, whoa, that is super duper interesting. So if Z doubles in price, we're still better off keeping our orders the way they are, even though the price will double. That is really, really interesting. And this is kind of fun because you start playing with money and production and orders and so forth. Okay. Example 3. I'm going to try, I hope I can, I might just give you the idea of 3, and then, because this video is getting long, I hesitate to make videos that are way too long. Now, I'm going to use the letters, so the vector x will be x, y, z, w. I know this is kind of weird because the last letter in the alphabet is z, and then I put w after that. And my reasoning is because I'm using x as my first letter. So I know what I should do is really do x1, x2, x3, and x4, because then it's clear, okay, this is the first one, that's the last one of the 4 of them. But I'm going to stick with x, y, z, w, only because I don't want to start putting indexes that I have to read, and I might not read them so easily as the letters x, y, z, w. So please be aware, this is the order in which I'm writing x, y, z, w, even though kind of doesn't make sense because w is not the last letter in the alphabet. Okay, so the equations are x plus 2y plus 3z plus 4w equals 12. See, I'm just going to explain this, and then I'm going to ask you to please do this problem. 3x plus 3y plus 4z plus 6w equals 24. 4x plus 2y plus 3z plus 4w equals 24. So we got 4, and I cannot draw this anymore. If we had 3 variables, you know, x, y, and z, we can have 3 dimensions, which I can draw 4 dimensions. I refuse to draw 4 dimensions. I cannot draw 4 dimensions. So this has to be done pretty much by just the math. I'm just going to check the coefficients. So 1, 2, 3, 4, 12, 3, 3, 4, 6, 24, 4, 2, 3, 4, 24 again. So we want to solve this system of equations. We have 3 unknowns and 4 variables. So that means there's going to be at least 1 free variable, just like we did have. Now there's going to be restrictions on that variable. Keep in mind the restrictions, because all the x, y, and z's have to be positive. All of those guys have to be no less than 0. And that will cause us to have restrictions. Pay close attention to those restrictions. Okay, so the cost vector so part A let's have a cost vector of 1, 1, 1, 1. So $1 per X, per Y, per Z, per W, and see what that does. What I'm going to suggest, part B, is find a cost vector C, so another one, it could be 2, 1, whichever, so that solution is not the same as in A, in this cost. And the one thing that I want to add to this is, in both cases, in both A, B, find minimum cost. So you want to find the dollar amount and also the vector that produces the production vector that produces, or the order vector that produces that cost. I think you are going to be okay, that this problem 3 should not give you major headaches. It's just the same as problem 2, just a little longer, but it shouldn't give you much of a headache. Okay, so cost, find another cost vector so that the solution is different, and that's it. That's problem 3. Problem 4. Okay, I'm going to use problem 3. So problem 4. We're going to change the equations. Instead of those 3, we're going to have 2 equations, and only 2 equations, x plus 2y plus 3z plus 4w equals 12. So I'm copying the first equation, and I'm going to copy the second equation, 3x plus 3y plus 4z plus 6w equals 24. So the first 2 equations, ignore the third equation. This is example 4. Part A. Minimize the cost where the cost is the same, $1 per letter. And you may be thinking, well, isn't that? No. It's not going to be the same. See, when we have 3 equations and 4 variables, and we start row reducing it, hopefully we'll end up with 1, 1, 1, and then W is going to be our free variable. And then we end up with a constant and a slope with a W, and then that tells us whether you're going to have a maximum or minimum based on W. With 2 equations only, the best we can hope for is that that's going to be 1, 1 when we row reduce it, but then we're going to have 2 free variables. See, in problem 3, okay, we will probably end up with, okay, the cost being, I don't know, some number, for lack of a better, I'm just going to call it MW plus B. It's like the line. If M is a slope, if the M is positive, then the smaller the W, the smaller the cost. If M is negative, the larger the W, the smaller the cost. So this is pretty straightforward. In problem 4, in contrast, we will probably end up with, okay, the cost being M1. So this is interesting. It's going to be M1 of Z. So a slope for Z plus a slope for W plus some B. This B has nothing to do with those two. It's just another B. Yeah. Okay, so now the problem is complicated again. What I suggest you do is maximize this, maximize that, figure it out. This is a challenge, though. It's a reasonable challenge. It's not a super difficult challenge, but it is a reasonable challenge. You got to figure out what combination of Z and W is going to minimize the cost. Now, the nice thing about this is that your equations started with 4 variables, and now we have reduced the problem to 2 variables only, as opposed to 4. Yeah. So please figure this out. Now, the reason why I am not telling you how to do this is because I want to emphasize the why. Remember, we had this question, if I just gave you the quadratic formula without telling you why, well, anybody can do that. In fact, linear programming problems I'm sure you can find software somewhere where they can solve the problem. You just enter the matrices and then you're all set. But we really want to have an understanding of why things are working the way they are. And one of the ways in which we can do that is by actually solving the problem without formulas, just by working our way through the matrices and the solutions and the way the solutions look like and so forth. So please do problem number 3 in this video, which has 2 parts, A and B, and then do problem number 4, which doesn't have part B, just the cost. You don't have to find another, so there's no part B, just A, where you don't have to find another cost vector. If you find the best cost, absolutely the best cost, then you're good. All right, with this, we're gonna finish the video.